Hi, I am Ritik Maiti, a student of physics, and I have completed my masters from Jamia Millia Islamia New Delhi last year. I am making a video about moment of inertia, the topic of moment of inertia today, and we all know that it's a demon that all student faces. It's quite hard to conceptualize, and it's a little bit on the tougher side to figure out the problems and the solutions. So let's talk about moment of inertia today, and hopefully I'll by the end of the video I'll be able to simplify it. So first of all, let's talk about inertia. What is inertia? We have all talked about inertia, or we have all been taught inertia in Newton's first law of motion. So inertia in linear motion is basically the tendency of a body of not changing its state of dynamics. What do I mean by dynamical state or state of dynamics? Is that if it is in rest, it will not be or it will not want to change its state from rest to motion or uniform motion. Or if it is in uniform motion with if it is in a linear motion if it has a linear motion with a uniform speed, which we call that as motion with uniform velocity, it will not be able to change that state as well. So in linear motion, basically the tendency of a body, the tendency of a body to not change its dynamical state. Now, what do we need to change a body's dynamical state? That is force from the first law of motion, and the second law of motion gives us the formula or the mathematical expression of force, that is F equals to ma. So this means provided I give a force or I apply a force of F on a body of mass m, that generates an acceleration of a, it will change the dynamical state of the system of the body. If it was at rest, it will continue to move with a uniform acceleration of a. So by applying force, we can change the dynamical system of a body. So this is where the concept of inertia comes, as the amount of force that will be needed to make or to change the dynamical system of a body is directly proportional to the mass of the system. So amount of inertia, or the inertia, is directly proportional to the mass of the system. Or we can say in other sense that the inertia of a body is a virtue that has been given to it, or an inherent property of a body or an object that has been given to it by mass. It's a pretty inherent property of an object. Now similarly, if there is a inertia, or there are two kinds of inertia, I forgot to mention, there are two kinds of inertia that we have been talking, or we have talked about in Newton's laws of motion, that is inertia of rest and inertia of motion. Inertia of rest and motion. So inertia of rest is basically if the body is at rest, it will try to stay at rest. That is the inertia of rest. And inertia of motion is basically if the body is in uniform motion, or motion in uniform velocity, or it is moving with a constant speed in a linear direction, then it will be called that the body is moving with uniform velocity. And this motion, the body will resist to change its dynamical state, or precise this state, if it is not acted upon by a force, by an external force. So there are two kinds of inertias. Similarly, when we are talking about rotational motion. Now motion cannot just be only linear, it can be rotational, it can be any kind, it can be a mix of linear motion or translational motion and a rotational motion. So for rotational motion we need torque to make or to give an acceleration to the body. Now we have all known in the chapter of circular motion or rotations, or where we have encountered torque first, we already know that torque is a similar quantity. I mean, torque is very much similar to force, and it takes the role of force in case of rotational motion. So torque creates an angular acceleration that gives us or gives the body a rotational dynamics. Now the inertia that is involved in this rotational motion is called moment of inertia. Now in case of linear motion, we know that, or we have seen that, the mass of the body is important. The mass of the body is very important for the inertia of existence, or how big the inertia would be. In case of rotational motion, not only the amount of mass but the distribution of mass about the axis of rotation is very important, and this is how the inertia will be defined in terms of the distribution of mass about the axis of rotation. Now two very big words, let me just simplify it. So there is a body like this, and let's say this is revolving around this axis, or being rotating, not revolving, it is rotating about this axis with the angular velocity omega. And let's say this axis is some AB axis. Now the moment of inertia of this axis would not just be dependent on the mass, that is, the if the mass of the body is m, it would not only be it will not only be dependent on the mass m, it will be dependent on the distribution of mass. I mean, if I that means if I take the body to be an assembly of many particles, then the particles will be at different distances from the axis of rotation. Let's say r1, r2, r3, and some ith particle would be at ri distance. So the way these particles are distributed, that will also be very important in terms of determining the moment of inertia of a system. Now let us define moment of inertia. The moment of inertia is defined as moment of inertia, I am writing it in a shorthand notation, mi, is defined as the product of mass of a particle and the square of the distance from the axis of rotation to the position of the particle. So let's say I have a distribution of mass, I have a distribution of mass with a total mass of m, and the particles are distributed in such way that m1, m2, m3, this is mi, and the distances are r1, r2, r3 and ri. Then the moment of inertia would be sorry for the spelling mistake, inertia of the body would be I equals sum over I mi ri squared, or we can write it as, first I should have written the component form, or in more elaborate way, that is m1 r1 squared plus m2 r2 squared plus m3 r3 squared, plus that is basically I mi ri squared. Okay, now let's not get confused on the notations. We can write ri squared as this as well. I know that those of you who have just started studying vector, you already know that the ri squared, or any square of a vector, is a scalar. Square of a vector is a scalar, so you are all writing it as ri squared. But yes, we can write it as this, and this means scalar, and this notation is widely followed if you get to higher books of higher classes. So there is not a problem at all on this matter. Okay, now we have defined the moment of inertia. So okay, now if r is a point in as r can be a point, in 2D or 3D, and we have to express r in, okay, this r I have written it by mistake, r in Cartesian coordinates accordingly. If it's in 2D, then ri squared equals xi square plus yi square plus xi square, xi square plus yi square, and for 3D it is ri squared is basically xi squared plus yi squared plus zi squared. Okay, now there comes another quantity that is known as the radius of gyration. It is defined as the distance from the axis of rotation at which, if the whole mass of the body were supposed to be concentrated, then the moment of inertia would be same as the moment of inertia with the actual distribution of the mass of the body of the small particles. What does it mean? Let's see. Radius of gyration. If the body, it means the distribution of mass. If the body, I am trying to write it in a easier language, and please don't write it in this language in your examination. That will be a disaster if you do. It's just to help you understand. If the body is a point mass, let's say a point mass, if the body is a point mass, let's say this point, and it's at some distance k from the axis of rotation. Let's say this is the point and this is the axis of rotation, and this distance is k. Now we are saying that, or the radius of gyration is defined such that if instead of this point mass the body was at its original form, that is the assembly of many point masses, or the system of particles, you can say that. System of particles is a better word to use here. If the body was a system of particles and this is the axis of rotation, again this can be anywhere. Now this is R1 and let's say this is Ri. I am feeling lazy today, what can I do? This is Ri. So if this is the case of the body, then what will happen? The moment of inertia I can be written as, or is written as, sum over mi Ri squared, okay, or we can write it as the way you write also, mi Ri squared. And from the previous section where I have done this, here I can write the moment of inertia I as sum over mi. Sum over mi is being m, that is the total mass of the body which is situated at a point at a distance k. So mi k squared. Now from here sum over mi will be capital M, that is the total mass of the body, and k squared. Okay. So here just equate both the expressions and we get m k squared equals sum over mi Ri squared. Okay. Now here comes another assumption. If this is in general case, I'm sorry, this is in general case. Now if m1 equals m2 equals m3, we are taking that all the system of particles, I mean all the particles in the system of particle have the same mass, then we can write the previous formula as mk square equals m, or rather sum over m I Ri squared, which can be written as m can be written as R will get commoned out, then m sum over Ri squared. Now if let's say there are n particles, then I can write this m as m by n. If there are n particles, I can write this m as m by n, and this is basically, if I remove this summation sign, then I will get r1 squared plus r2 squared plus dot 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 plus, let's say rn r dot 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 plus, this will go till rn, I am having a problem with space, rn squared divided by n. Okay, this n I am putting this n over there, so I am getting m k squared equals m r1 squared plus r2 squared plus rn squared divided by n. So m gets cancelled out. This gives me k equals root over r1 squared plus r2 squared plus r3 squared plus rn squared divided by rn. So this value or this expression is the radius of gyration. This k is the radius of gyration. Now it is interesting to see that k can be written as root over sum over I ri square divided by n. Now this sum over I ri square divided by n, this is basically a new quantity this kind of quantity is very much used in statistics, and you will get to see this kind of quantity in thermal physics as well, where you are trying to find the root mean square velocity of a system of gas. So this is the root mean square distance. So what we are getting is, this is the square, this is under the root, this is mean square distance, and as we are taking a root of the expression, we are taking the root mean square distance, and this root mean square distance is called the radius of gyration. Okay, now the radius of gyration is completed. Now there are two theorems regarding the moment of inertia. They are very much interesting things to study, really. We will see that how we are using the perpendicularity and the parallel to perpendicular axis or one parallel axis in our moment of inertia cases, and see that we can go from moment of inertia about once a certain axis to the parallel or to the perpendicular axis of that body, or of that axis for that body. Now let's say first let us do perpendicular axis theorem. Perpendicular axis theorem. Perpendicular axis theorem says that if a body is like this, let's say this is a three-dimensional plane which is x-axis, y-axis and z-axis. X-axis is rotating, the body is rotating over x-axis like this, y-axis like this, and z-axis like this with different angular velocities, and the body is lying over here. For now, let's say that this is a lamina. Lamina means a two-dimensional flat object. Now let's say there is a point, this point is mi point, which is at some ri distance from the origin of the coordinate system. Now the distance, the perpendicular distance from x-axis to the point to this point would be xi, and from y-axis would be yi. Okay, I have written it wrong. From x-axis would be yi, and from y-axis would be xi, which is pretty evident. Y and okay, let me draw it in a better way and in a bigger picture. Okay. This diagram is very important, so let me draw it in a better way. So this is x-axis, this is y-axis, and this is z-axis. And this is the laminal body. This is the ith particle that has the mass mi, which is at a distance ri, and this is some yi distance, as this is the y-axis and this distance is perpendicular to the y-axis, parallel to the y-axis. We have to write it as yi, and this distance is xi. Okay, now for the rotation, about x-axis, the moment of inertia is what? Ix, that is mi yi squared. Now just put a sum over here for the system of particles. Okay. Similarly, for Iy, that is the moment of inertia for the rotation about y axis, would be sum over I mi xi. See, sorry, xi squared. See, mi xi squared. This is the for y axis and this is for x axis. Because when around x axis it is rotating, the perpendicular distance would be y from the origin, or from the rotation of axis of rotation. And for z, this is very important. Look at the picture again. For z axis, the perpendicular distance from the axis of rotation would be what? Mi ri squared. Then ri is the perpendicular distance from the axis of rotation. So I have to write it as sum over I mi ri squared. Now what is ri? Ri is basically root of ri is vector addition of xi and yi. That is, the magnitude will be given by xi squared plus yi squared. So mi would give me xi squared plus yi squared. So if I do the sum, what I get? Ix plus Iy. So thus I have proven the perpendicular axis theorem. Iz, that is a perpendicular, that is an axis that is perpendicular to both x and y, is Ix plus Iy. Let's do this thing for parallel axis as well. So let's say I have a laminal body again. This is the center of mass of the body, and there is an axis, let's say IC is passing through this, and I have to figure out the moment of inertia about this axis. That, let's say this is some axis I. Axis I. The moment of inertia about this axis would be I, and this is a d distance from this axis through the center of mass. And this parallel axis theorem actually states that if there is an axis that is parallel to the axis that passes through the center of mass of a body, then the moment of inertia about that parallel axis, that is parallel axis or the new axis, in this case this is this axis, would be equal to the center of the moment of inertia about the center of mass of that object, plus the total mass of the body multiplied by this distance squared. That means the moment of inertia about this new axis I would be IC plus md squared. Now let's see how can we prove that. So let's say I have an object, the center of mass lies somewhere here. Let's say this is the center of mass I, this is the center of mass C, and this is the moment of, I have to figure out the moment of inertia, and this distance is d. Okay, let's consider a point that is Ri. Now here is the origin, as this is the axis of rotation, and the distance, this distance is d, and the distance of that particle from the point of axis or point of origin or the axis of rotation would be, let's say, capital Ri. Now if I broaden this picture up over here, what I will get is I have two vectors like this, and this is the resultant vector from the triangle law. So we can easily write that Ri is basically Ri we can write it as C, RIC plus D. Now remember that D is a constant. Now it's basically very easy to do that. The moment of inertia I about the new axis would be sum over I mi capital Ri squared. Okay. Now what is capital I? Capital I is basically the distance from the center of distance of the object. I mean distance of the distance between two axes of rotations, and the distance of that point mass from the center of mass, and square of that. If I do this, what I will get is, I am doing a little bit of step jump over here, mi d squared plus sum over I to mi d ric plus sum over I mi ric squared. Now see, MIRIC squared, this gives me IC, the moment of inertia about axis of rotation. Let's write it over here, IC plus D, this D squared, in this D squared, this D squared is a constant, so this will come out of the summation. So I will get a sum over I mi plus I have 2 in this expression, that will come out of course, and that D, as it is a constant, will come out as well. So 2D sum over I mi ric. Now this is 0. We have learned this in the chapter of center of mass. This is 0. The distribution of mass about the center of mass, that will give me 0 if it is been product, it is been done. I mean if I do a product of mass and the position vectors of the center of about the center of mass. This is a very important property to remember. So as this gives me a 0, I am getting IC plus m d squared. This is basically the parallel axis theorem. Now I will do just 2 things and then I will end this video. First thing I will do is, I will show how to use this these 2 theorems, and then I will calculate the moment of inertia of a ring for a, I mean basically the moment of inertia for a continuous mass distribution. I mean a point to remember is basically that would actually involve some integration techniques that is yet unfamiliar to my audiences from class 11th and 12th, but for my higher audiences for higher classes who are in BSc or MSc, that is pretty piece of cake for them. Okay, let's start. So the moment of inertia of a ring, the moment of inertia of a ring about the center ring about an axis that is going through the center and perpendicular, this is the perpendicular sine, perpendicular to the plane of the ring. So first let's start with the formula. The moment of inertia of this ring about this axis, that is basically, this is a ring of radius r, and let's say the mass of the ring is m, then the moment of inertia of this ring would be I equals m r square. Now we can say that this axis is z axis, so Iz equals mr square. Now from here we can actually figure out the moment of inertia about x axis and y axis. How? Now see, there is a symmetry, and symmetries are very much important for studying physics. So symmetry is about z axis. So basically if I rotate around or go around z axis or rotate around z axis on this ring, there will be no difference that I will be able to find if the mass distribution, I mean the mass at every point on this ring, is equal. This specifically means that the moment of inertia about the x axis would be equal to the moment of inertia about y axis. This statement can also be understood by this in this way, that if the ring is rotating around this axis, or if the ring is rotating around this axis, these both axes are in horizontal plane, on horizontal plane. So both the axis, in case of both the axes, I will not find any difference whatsoever. This is called the symmetry about z axis, or in many cases we call it azimuthal symmetry as well. I guess it is azimuthal symmetry. Okay, yeah, I don't remember. No, I don't remember the name of the symmetry quite well right now, but I will clarify later. So Ix equals Iy. So basically, from the perpendicular theorem, we can say that Iz equals, we already have Ix plus Iy. That is what? 2Ix we will get as Ix equals Iy. So Ix would be Iy, both are equal, that would be Iz by 2, and that is half m r squared. Similarly, I can find moment of inertia, let's say about an axis that is going through this point on the edge of the ring, or passing through this point, that is r. So we already know that the let's say r would be moment of inertia about z plus m into r squared, that is basically 2m r squared. Now the final bit of this session, that is I will be trying to figure out the moment of inertia of this ring about the z axis, of course. Let's say this is the z axis. The moment of inertia is given by I equals sum over I mi ri squared. Now this is, let's say this is ri. Let's take a little bit on this ring, little line segment on this ring, and let's say this ring has a uniform mass distribution lambda. So the total mass m total would be lambda into 2 pi r being the radius of the ring. Acha, this bit of line segment would be r d theta. And how this is m into 2 pi r, lambda into 2 pi r, let me make it clear. The whole 2 pi r length of the ring is carrying the total mass m of the ring. So the unit mass lambda is given by m divided by 2 pi r. So m will be equal to lambda multiplied by 2 pi r. Okay. Now what we are going to do is, as from this expression, we will be trying to write for the expression for continuous distribution, that will be given by an integration sign, that will be written as r squared dm. Okay. Now this dm, we know that dm can be written as the amount of mass that is being carried out by the unit length of the ring, that is lambda, the mass density or the line mass density, you can say that, or mass per unit length, that is lambda, multiplied by this little segment we have taken, that is r d theta. Acha, this in this case this will be capital R. In general, I equals integral r square dm, but as in this case we are taking a circular thing, there will be r will be constant in this case, in this particular case. So r d theta, so r lambda r d theta. So what I will do is, now I will get is lambda r cube d theta. Okay, I have mixed up capital R and small r. This will be capital R, this will be capital R, this will be r cube d theta. So basically lambda r cube integral d theta, this will give me lambda r cube into 2 pi. What happened? I am getting 2 pi lambda r cube, but I have written a formula that says, that is mr square, the moment of inertia about z axis. This is precisely m1 square. Let's see. Lambda is m by 2 pi r, and the r cube stays over here. This gives me r squared, and 2 pi gets cancelled out, so we get I equals m r squared. Okay, so this is it for moments of inertia. Please comment, like and share, and support my channel to grow. I will come with another simplified version of some complex topics. Please let me know how. Please in the comment section, please give your precious feedback. Okay, bye.